Hello, everybody. Listening to this first webinar in a series of webinars organized by the European Machine Vision Association, or in short EMVA, about its 1288 standard to characterize cameras in an objective way. The purpose of this series of webinars is to make you aware of this standard and to give you everything at hand you need to know so that you, for your specific application, can make educated selections of the best possible camera to be used. In today's seminar, in the first one here, we will simply address the question, why actually is an image sensor not perfect? Because if it would be perfect, we would not need a standard at all. I could also put this question in a little bit different way. What are actually the effects which degrade the signal of a camera? And I will do that basically in 3 steps. The first will be a little bit of a risky experiment because I decided to do really some live demos. So we will simply take a camera and look at its signal and see whether we could see any degradation of the signal. And after we have done that in different directions, we will then look basically for the purpose of the EMVA 1288 standard. And at the end, you have the opportunity to ask also some questions. So let me basically switch now to the demos. And I will do that basically by taking here one of these many cameras you can buy now on the market. Let me just get the screen ready here. And you see I have the cap here on the camera, and this is actually a screen where you then can see the image. And of course I have first to put it into live acquisition. Now actually a live acquisition is running. You can see that here down at the counter. And not surprisingly, you don't see anything because we receive no signal. And it appears that this signal is almost perfectly black, so nothing to complain about. Well, let's do a little bit more. I remove the cap, and now let's look here at a small object where I put the camera. You see it's obviously a little bit out of focus. So let's try to focus this object. Well, you see now it's much better. And looking at the eye on this image, you will say, well, it looks actually perfect. Especially you don't see something which is a very common phenomenon for any type of measurements. Any measurements typically contain some noise. And the trouble is, not the trouble is, so to speak, we don't see any noise with our eye. But the problem is that our eye is simply not sensitive enough to see that noise. I would like to demonstrate that now. If I take here simply a row out of this object, and now I draw basically a line where you see an intensity profile along the screen line in the image. And now, of course, if I move the camera, you see changes, but I try to fix them. And still you can see that there is some fluctuations in the signal. So that means don't trust your eye if you want to detect noise. The noise, of course, is still quite low. But the eye is not sensitive to detect it. But for many measurements, of course, it still is a noise you can see, and it's we need some tools to measure actually the level of this noise. Let's try a small experiment. You see the noise. If you look a little bit more careful, you can even see in this profile. Let me go here. This is the dark part, very small changes, whereas in the brighter part, obviously there is a little bit more noise. So obviously the noise is even a little bit more complicated. It is not simply constant and gray value independent, but obviously it seems to depend on the gray value. And now we can say, well, this is a dark part. I want to see it a little bit better. And I simply do the following. I change now. I have the minimum gain now of the camera, and let's increase the gain by 6 dB or a factor of 2. Now you see everything gets brighter. And well, the signal has increased here. If you look again into this small part, but also the noise level is now more visible, as you can clearly see. Well, let's even get the gain here to the maximum analog gain you can put for this camera, which is 24 or a factor of 16. Now, of course, you have a almost completely supersaturated image. So let's simply close the aperture to come to the same level again. So the camera now receives much less light, but the signal is very much noisy. So you cannot say simply, well, all I need is a bright image. But obviously what we have to analyze in detail to look for the quality of a camera is basically how much noise I do have in relation to the signal. And obviously it is changing also with the gain. So I have less now information from this object, but obviously more noise because I have increased the gain. So this is one thing we have for sure to analyze in much detail. We can do a little bit. Now I made it again completely dark. And what I will show you now, let's go to the following. We will now switch off this continuous background grabbing. And I would like now to measure a little bit how much noise and what is a mean signal. And this can be easily done by basically grabbing one image. Oops, I made a typo here. Now I grab an image and you can see here the value. It's a mean dark value now, which is indicated here of about 20 dN. And the noise is 8 plus minus 8. That is a standard deviation. So we have a signal of 20 and the noise is thing. And now let's just to demonstrate that we get the gain down to its original value. And now let's simply grab again an image. You see, we still have about the same signal because we do not receive, I have the cap on the camera, you don't receive any signal. You just see the dark value with the same exposure time. But since I have changed the gain, you see now a considerably lower standard deviation. It went down from about 8 dN, where the signal was fluctuating, to only about a tenth or so, 0.89 or 0.9, where its signal is now fluctuating. So obviously this kind of things must be done then if we want to characterize a camera. It must be done in the dark image, and it must also be done at every illumination level to see how this is changing with the degree of saturation we have in our camera. Now, the question is, or what we first can state now is, obviously we have one source of degradation, which is a simple case. Each time we take an image, we get a slightly different value, and this is called temporal noise. But there are other sources of noise or of degradation in the signal as well. And this has to do with the very simple fact that a camera here just does not get us one signal back, but we have actually millions of individual pixels, as they called, light-sensitive small sensors, and you cannot expect that they are totally equal. So it might be the case that each of these pixels has a little bit different dark value, and also that each of these pixels has a little bit different, for instance, sensitivity to light. So let's try to demonstrate that. Again, we have a dark image, but I have to run it again, so to get live imaging again. But now, of course, since we have a dark image, we cannot see anything. This is actually a 12-bit camera. So let's simply do the following. We can change the display range. We have seen the dark value is about 20, so let's take about 40. And now you can see actually, again, nicely, the temporal noise in this dark picture. And you can, on the other side, see that there is, well, almost not any change from pixel to pixel in the dark signal. At least the noise, the temporal noise is dominating it. Another important question for the quality of a camera will be, what is basically the relation between the temporal noise and also this non-uniformity, for instance, in the dark signal. So let's go back to our original and look now also for the question if we have really light in our image. Oops, let's do it this way, it's easier. Okay, so we have a black image now again. And so I remove the cap here again and look again at this object. And so, of course, doing this is not very interesting, or it's now very difficult to say without having a real constant illumination that there is actually any type of non-uniformity in the sensitivity, because we have different illumination and we have a different reflectivity of the object and all these kind of things. So obviously, to do things like that, I have a camera and a lens now, so let's maybe look just at this black white surface. Oh, now we have, of course, too much of light, so maybe what we do is I still open it completely and I change now the integration time. To get to a smaller value, just 1 millisecond now. Let me see. Oops, that was a wrong. I made a typo here. So now you can see, maybe I'll have it completely open, almost open. So let's increase, it was a little bit too much. Let's increase it. We have still a factor of 2 or so. That was too much. Let's take 1.8 or something like that. Yeah, now you see it. And if you look now at this image, you get the idea. Well, I have still noise, of course, because it's changing. Because I'm not very stable here with this, you will see also some fluctuations of the whole thing. But you might just see, well, obviously towards the edge here, it seems to be a little bit less bright. And now the trouble is, of course, well, is this caused really by the sensor, or is it caused by the lens? Because you all know, or probably of this effect, that towards the edge of an image, we will also get shading effects. That means that the intensity towards the edge gets smaller. So what we really should do is just remove the lens here, because then we have actually only the effect of the camera itself. And now, I have interesting phenomena, because the illumination here is a fluorescence light and they are flickering. That is what you see here now. So let's increase the exposure time to 10 milliseconds and see that then we have, of course, too much of the illumination. Then let's go to a less bright spot here. Now we have again not a completely inhomogeneous illumination, but you can at least see, it's obviously different now. And that clearly tells you we need also special equipment with very uniform illumination and without any lens to study basically the question of the inhomogeneity of the pixels. Also, of course, we have to get rid of the noise, the temporal noise, because the fluctuations are bearing a little bit here these inhomogeneities. And the only way to do that is averaging over many images. So, last thing, so we see for sure, if we want to compare different cameras, we not only have to look for the level of temporal noise which is in these cameras, but we have also to look for the degree of non-uniformity, both in the dark image and also in the sensitivity from pixel to pixel. So that was the second type of degradation we can have for a camera. And there is finally a third one, which has to do with the very simple effect that the camera collects also a signal when no light is actually hitting the pixels. And how can I demonstrate this in the best possible way? Well, to see it in the best possible way, the first idea is to get the gain as high as possible. So we go again to 24 dB. And I have now, let's just to be sure that we have a short integration time, 1.8 seconds. Let's maybe go down to 1 millisecond of exposure time, and then grab then just one image. And oh yes, of course, I cannot grab an image if this is in live display. That's when you demo effects, and now we have a signal of about 21, and dn plus minus 8 dn standard deviation. That is a temporal noise. So, and now what I do is I receive no light. So let's simply increase here the exposure time, well, let's say to 500 milliseconds, so 500 times larger exposure time. But we have no light, so you might expect nothing should happen. So let's grab another image, and takes a little bit longer now, of course. And now you see two interesting effects. Instead of about 20 dn, we have a mean signal actually of about 40. So we really receive more signal. So obviously there are effects going on in a camera that if you expose longer and longer, you will get also an increase in the signal. But that's not the only thing we can observe. The same we can observe is that also the noise is being increased. And we have not changed the gain and nothing. Just by this effect, we see obviously something like that. So that means this is a third type of degradation we can have for a camera signal, that there is a signal already without any light, and that this is increasing with the exposure time. So that is what I wanted to show you in a quick demo. And you probably have now all understood we really need good tools, good measuring equipment to measure all these effects I tried to demonstrate more qualitatively in a quantitative way. And that is basically all what the EMVA 1288 standard is about. And so let me quickly summarize what we have seen here is the demos clearly told you we have 3 types of degradation. One is simply that each time you measure a little bit different values, what is called temporal noise, and is obviously very critical how much temporal noise I do have in relation to the signal. That is one, obviously, quality criterion we have to measure in detail. And this as a function of different irradiation levels in our camera system. The second degradation are all the inhomogeneities. And there, of course, a very important question is the temporal noise the dominant degradation, or is it this change from pixel to pixel? And is it the same in the dark as in the bright parts of the image? All these things have to be studied. And finally, we obviously have a clear limitation what is the maximum exposure time we can take with a camera, because if we have only long enough exposure times, we will saturate our image also just with this what's called the dark current. So these 3 things have to be discussed in detail, and we will start with that in our next webinar. So I hope you have understood that it's really necessary that we need a standard for objective and comparable specification of cameras as a component, and I demonstrated you get, for instance, some shading by the lens, and if you want to know the shading only by the camera, you have to measure only the camera as a component. And there were standards out, these ISO standards are out, which make a complete system camera with basically lens plus camera, but these standards are more from the perspective of a human observer, so the image should just look good, whereas nothing was available basically to do that out of the perspective of industrial image processing and measuring technique, and that is what the 1288 is about. So 1288 is optimized for machine vision, whereas these ISO standards are system characterization basically of consumer products. You will see in the following 3 webinars that a lot of work by many companies went into that standard, who developed it for more than 13 years now. We have a broad international support, and it's not only because EMBA is a European organization, it's not only a European effort, but with this global it's a global G3 standard, and it accepted actually by AIA, by the Chinese Machine Vision Union, by GIA, and also by the VDMA. We have a stable release available, 3.1, which is now almost a little bit more, than almost 2 years out, and very much used. The basic thing with this new thing is that to make comparison now really easy, there is a 1-page summary sheet. I only show you a section here of that, where you find all the most important parameters, which you will learn in the following webinars, so that you can really use this standard sheet. So that concludes this very first webinar now on the standard 1288. We will have 3 more webinars. In the next one, I'm going to explain you all the parameters so that you can describe these degradations I demonstrated you today. And then we will go more and more into your application. So in the third one, I will explain you how to use the summary data sheet. And in the 4th webinar, we will finally then go to your application, take some typical applications, and basically make some selections what would be for this typical application the best camera to be used. So now you have the opportunity to ask some questions. If you are not ready to ask these questions right now, you can always also ask these questions later in the other webinars, or just send me please an email, and then I will actually put in my comments or will take care of what you have asked. Well, as long as no questions are coming in, I will quickly tell you I got actually two important hints already. One asked, well, this is now a camera basically in the visible range. Is the 1288 standard also applicable for cameras in the short wave infrared? And the answer is yes, of course. We have not all, at the moment not worked out all the details. This is actually work in progress going on in the standardization group, that we look for all the specific things which have to do then if we change now to a different wavelength. The same is of course true for in the UV. Everything what basically converts electromagnetic radiation into an electrical signal can be handled by the EMVA 1288 standard. So let's give you a chance still for half a minute or so if them questions are coming in. But I know the more questions will certainly come in when I go to the more quantitative description. That was now just a kind of introduction. Well, then let's conclude. And you certainly are interested actually where you can learn more about the standard, because as I told you, this webinar is basically for the purpose just to use the standard for your application. So to make it clear how easy it is actually to use that standard for your needs. And if you want to learn more, there is a good opportunity coming up very soon at the Vision Fair in early November. This is actually a picture of the International Machine Vision Standards booth from the last fair 2 years ago. But you will find a very similar large booth also on the Vision in this year. So I will be around basically most of the time at this booth. So that is a good opportunity if you want to talk to me personally. Then use opportunity to visit this International Machine Vision Standard booth. It does not only, of course, include EMVA 1288, but basically all the standards which have been issued by one of the G3 associations. And for those who want to look a little bit more in detail, there are two links here where you can get standard documents and also example data sheets. That is one thing. And for those who really want also to do their own measurements, so actually look at the standard not out of the perspective of a user of the camera, but of a developer, there will be a new series of hands-on seminars for those who really want to do the measurement, understand the measurements, see what can go wrong, to get practical exercise with real measurements we will take into these courses. And there will be actually in December one together with Framos in Munich. And next year in March, we will have a second course like this in Hanau here with Aaron. So I would like to thank you for your participation in this first webinar. We will continue with the second webinar tomorrow, again at 4:30 p.m. And I look forward to this next one, because then it gets really interesting. In that sense, we will learn how to put what I tried to explain here in a qualitative way with some, well, demos, how you can basically do this now quantitatively with all the tools which are available now with the EMBA 1288 standard. So see you tomorrow then for the second webinar. Oh, I see. Let me see. Thank you for this first webinar. There was a question. I would be interested to know what tool you are using to grab, display, and show horizontal profiles. Well, this is actually a software called Heurisco. That is one of the software packages which is available on the machine vision market, and that is also the software we use for all the EMVA 1288 measurements, and this is why you have all these nice tools included there. Even more, you can of course also look in numbers at these things. Maybe I can simply show that. If you have this image here, for instance, you can also have a tabular display. So you see now from the left upper corner really the direct digital values you have there. So a lot of interesting tools for all kind of things. And what I could do is I could add a link to these slides for this Heurisco software so that you can then also look in more detail at that. Thanks for that question. And well, that really concludes now this webinar. See you tomorrow at the same time.